So now let's look at the derivatives of logs. So the derivative with respect to x of log base a of x is 1 over x natural log of a. But what I want to do is I want to prove that that is the case. So let's actually prove that that's the limit, the derivative. So we're going to start with y equals log base a of x. In exponential form, this would be a to the y equals x. So we now have this, and we can do implicit differentiation, take the derivative with respect to x of both sides. We're using implicit differentiation because we aren't putting y by itself. We have y by itself, but we don't know what that derivative is. So we can use implicit differentiation to find this. The derivative of a to the y, we know that. That's a to the y times the natural log of a. But because of implicit differentiation, this is the derivative of the outside. Then we're going to multiply that by the derivative of the inside. And we don't know the derivative of y with respect to x. The best we can write is dy dx. That equals the derivative with respect to x of x, which is just 1. All right, so we just need to solve for dy dx. dy dx is equal to 1 over a to the y, natural log of a. But remember, a to the y was x. So we have 1 over x, natural log of a. So we just proved that. That is the proof for it. We now can use it because we know it. What if the base is e? So let's look at the derivative with respect to x of the natural log of x. Because remember, natural log of x is log base e. So that would be 1 over x, natural log of e, because now my base is e. But remember, the natural log of e is just 1. So this is just 1 over x. All right. So we now know the derivative of natural log of x is just 1 over x. All right, let's look at the derivative of cosine of natural log of x. Again, this is cosine of natural log of x, so that's the chain rule. The derivative of the outside is minus sine of x, or minus sine of something, and the something is natural log of x. Then multiply by the derivative of the inside. The derivative of natural log is 1 over x. All right, so now let's look at the derivative of the natural log of this fifth root of 3x plus 2. We can do this with chain rule if we wanted to, but I want to also remind you that I can do something with this a little bit. First off, I don't like fifth roots, so write this as the natural log of 3x plus 2 to the 1/5 power. And then I remember there's a really nice property of logs. And that property of logs is I can actually take that power out in front. So that means I can become the derivative with respect to x of 1/5 natural log of 3x plus 2. So granted, I'm still using the chain rule, but it's not as ugly as it was before. Before it was going to be the chain rule and the chain rule. This is just one chain rule. So the nice thing when you're using natural logs is remember your properties of logs. So it can simplify these things a little bit. So the derivative of natural log is 1 over whatever. So we've got 1 over whatever times the derivative of the whatever. And the derivative of the whatever, in this case, 3x plus 2, the derivative is 3. The whatever is 3x plus 2. So we end up with 3/5 times 1 over 3x plus 2. And that's much easier than if we'd done it the long way. So let's take another problem. Here we have y equals log base 10 of x over x minus 1. Now I have to find out what y prime is, but before I do that, I want to think about, again, what would this be? This would be the log base 10 of x minus log base 10 of x minus 1. So again, remember your properties. The log of a quotient is log of 1 of the top minus the log of the bottom. So let's use those rules. So now we want to find y prime. So the derivative of log base 10 of x is 1 over x, whatever's inside, times the natural log of that base. The base is 10. Minus 1 over whatever's inside, x minus 1, times the natural log of the base, and then times the derivative of the inside, but the derivative of the inside is just 1. So we get that we have 1 over x, natural log of 10, minus 1 over x minus 1, natural log of 10. So that's a little bit easier, a little bit simpler to do it this way. So let's look at another one. Let's take the derivative of this. Again, I would simplify this a little bit. This is the natural log of, sorry, I have derivative with the g of u is the natural log of the square root of 3u plus 2 over 3u minus 2. So we're going to do this as the natural log of 3u plus 2 over 3u minus 2, all to the 1/2 power. Well, property of log, I can bring that 1/2 out front. So it's the natural log of 3u plus 2 over 3u minus 2. And again, the natural log or the log of a quotient is the log of the top minus the log of the bottom. So we have 1/2 natural log of the top, 3u plus 2, minus the natural log of the bottom, 3u minus 2. All right, so now when I go to take the derivative, it's a little bit easier to do. So again, when you're dealing with logs, it's easier to use your properties of logs. So we're taking the derivative. The derivative of the first one is the natural log of whatever. So it's 1, the derivative of that is 1 over the whatever, times the derivative of the whatever. The derivative of 3u plus 2 is 3. Minus, again, we have natural log of 3u minus 2, so that'd be 1 over the whatever, 3u minus 2, times the derivative of the whatever. Remember, the whole thing's times 1/2, so put the parentheses around the whole thing. And just to simplify it just a little bit, we have 1/2 times 3 over 3u plus 2 minus 3 over 3u minus 2. And that was a little bit easier than trying to do it the long way. So we can, you could do it the long way. I'm not going to. So that was an or thing. You get the same answer if you did it the other way. They may not be perfectly the same answer, but they'd be arithmetically or algebraically the same. Let's try another one. Let's look at f of x equals the natural log of the absolute value of x. So remember, absolute value means that if x is bigger than 0, we can just drop the absolute value bar. So we can get that f of x is equal to the natural log of x if x is bigger than 0. If x is less than 0, then you get the absolute value is negative of whatever is inside. So it's the natural log of negative x, as long as x is less than 0. Notice that it includes 0, because remember, you can't take the natural log of a negative of a 0. You also can't take the natural log of a negative number. So the x being less than 0, that's why we also need that negative sign there, makes it positive. So now let's find the derivative. So the derivative of natural log of x is 1 over x, if x is greater than 0. The derivative of natural log of negative x is 1 over negative x. But now we have a chain rule problem, because the derivative of natural log is 1 over the something times the derivative of the something. The derivative of negative x is negative 1. That's if x is less than 0. So we end up with that this is equal to 1 over x if x is greater than 0, and negative 1 over negative x is just 1 over x if x is less than 0. So looking at this, we realize that actually the derivative of the natural log of the absolute value of x is just the same as 1 over x. This becomes important a little bit later when we get into undoing derivatives. But right now, just realize that the derivative of the natural log of the absolute value of x is just 1 over x also. Natural logs have some really nice properties. So if we have really nasty equations and we want to find the derivative of that function that's really kind of involved, we can actually use logarithms to help us do that. It's what we call logarithmic differentiation. And so I have y equals the 4th root of x squared plus 1 over x squared minus 1. I can do this using the chain rule and the quotient rule without any trouble. I could even make this into the 4th root of x squared plus 2 over the 4th root of x squared minus 2, and then write them as one is negative exponent, and then find the derivative with that product. So I could even do it that way. But I'm going to use logarithmic differentiation. So I want to show you how this works. We can take the natural log of both sides of an equation anytime we want. So since our function is y equals the 4th root of x squared plus 1 over x squared minus 1, we can think of this as an equation in a way and take the natural log of both sides. We're going to take that, it's not really an equation, but we can take the natural log of both sides of this function. So we have the natural log of y equals the natural log of the 4th root of x squared plus 1 over x squared minus 1. Well, again, the fourth root I can write as a power function. This would be x squared plus 1 over x squared minus 1 to the 1/4 power. So we have the natural log of that. And that equals the natural log of y. And then remember that I can bring that 1/4 down in front. And I also have the natural log of a quotient. And I can separate that out into the natural log of the top minus the natural log of the bottom. So I'll do that in one step. So I'll bring the 1/4 out in front. That was a 1/4 there. I wrote a 1/2 by accident. So bringing the 1/4 out in front, and then I have the natural log of x squared plus 1 minus the natural log of x squared minus 1. Okay. All right. So we now have that. And now we can think about taking the derivative of both sides of the equation. Okay. So we're going to go ahead and do that. We're going to take the derivative of both sides of the equation with respect to x. So we have the derivative of the natural log of y equals the derivative with respect to x of the 1/4 of the natural log of x squared plus 1 minus the natural log of x squared minus 1. Well, the derivative with respect to x of the natural log of y is, again, we don't have y by itself, so it's the derivative of the outside. The derivative of natural log is 1 over the something, so 1 over y, times the derivative of the something, which is the dy dx. Because we don't know what the derivative of y is, so we're going to write it as dy dx. The derivative of the other side, we've got this 1/4. The derivative of natural log of 1 over natural log of x squared plus 1 is 1 over the something, x squared plus 1, times the derivative of the inside of the something, which is 2x, minus, again, the derivative of natural log of x squared minus 1 would be 1 over x squared minus 1, times the derivative of the inside, which is 2x again. All right, so now let's see what we have. We have the derivative of y with respect to x is equal to y times 1/4. And we actually have a 2 there, so we can cancel the 1/4 and make that 1/2. Cancel those 2's. So we have 1/2, and we're going to have x over x squared plus 1 minus x over x squared minus 1. But now I got to remember, I don't want a y in there. I want to know what the derivative of y with respect to x is. Y was equal to, way at the top, y was equal to the 4th root of x squared plus 1 over x squared minus 1. So we'll replace that y with what it's equal to. It's equal to the 4th root of x squared plus 1 over x squared minus 1 times the 1/2 times x over x squared plus 1 minus x over x squared minus 1. Now, if you'd done this the other way of doing the chain rule and quotient rule and a bunch of other stuff, you get the same answer. They wouldn't look exactly the same. Algebraically, they'd be the same, but they're a little different right here. So this is a way to do it, just to make life a little bit easier on you. Let's look at another example. Here we have y equals x to the 1 over x. And again, I want to find the derivative of y with respect to x. This one I can't do any other way. This is not a power function because it's x to the 1 over x. Power functions are x to a constant. This is not an exponential because it's x to the 1 over x. And an exponential, the base is a constant. So this isn't anything. This is actually kind of a strange function. And what we have to do is figure out how to do this. And the only way to find this derivative is actually using logarithmic differentiation. So we're going to take the natural log of both sides. And I'm using the natural log so I don't have to deal with the log base of the base. It's just easier to use the natural log on this. I'm going to take the natural log, and when I do that, I've got the natural log of y equals the natural log of x to the 1 over x. I can bring that 1 over x out in front because the log of x to a power, I can bring that power out in front. So I'm going to do that. Now I'm going to take the derivative with respect to x of both sides of the equation. And see where I end up with here. Okay, so the derivative of natural log of y, we've done this several times. It's going to be 1 over the something, in this case the y, times the derivative of the something, which is dy dx, because we don't know what the derivative of y with respect to x is. Then we have the derivative of 1 over x times the natural log of x. We're going to have to use the product rule because, again, we have a multiplication there. So the product rule is the derivative of the first one. The derivative of 1 over x. I would probably go ahead and we'll rewrite this before we find that derivative. 1 over x I'd write as x to the minus 1. It just makes life a little bit easier to look at that way. So we now can find the derivative of that product. Bring the power down, minus x to the minus 2 times the natural log of x, using the product rule, the derivative of the first times the second, plus the first, 1 over x to the negative 1 times the derivative of natural log, which is 1 over x. And so what I have now is I have 1 over y dy dx is equal to negative 1 over x squared, natural log of x, plus 1 over x times 1 over x is 1 over x squared. So if you want to, first we do want dy dx by itself, so we take dy dx by itself by multiplying both sides by y. And then we have negative natural log of x plus 1 over x squared. But I don't want this y here. What was y equal to? So go back up to the top, y was equal to x to the 1 over x. So we replace that, so we have x to the 1 over x times negative natural log of x plus 1 over x squared. And that's the only way to do that derivative. The last thing I want to do is just show you the proof of the power rule. We've never actually really proven it. We've done sort of a proof, but only if we assume that x was a positive number, a positive integer actually. We want to do it for anything. So in this case, n is any real number, except of course we wouldn't have 0 there because x is 0 is 1, and that's boring. And so we wouldn't have that, but it's any other number you can look at. And I want to find that derivative. Again, what I'm going to do is I'm going to take the natural log of both sides of the equation and see what I get. Okay. I know what the derivative already is, but I want to prove it. So we're going to write word proof here, so we know we're doing the proof. So I took the natural log of both sides, and then I'm going to take the derivative of both sides. But remember, when I take the natural log of x to the n, I can bring that n out in front. So I'm going to bring that n out in front. So I have n times the natural log of x. All right. Again, the derivative of natural log of y is 1 over the something times the derivative of the something. So it's 1 over y times the derivative of y with respect to x. The derivative of n times the natural log of x, well, n is a constant, so it just comes out, and the derivative of natural log of x is 1 over x. So we now have dy dx is equal to y times n times 1 over x. But now remember, what was y equal to? Going back to the top, y was equal to x to the n. So put back in what the y was, x to the n times 1 over x. And now I see I can simplify this just a little bit. X to the n times 1 over x is x to the n minus 1. And there was the proof. So that is how we prove that the power rule works.